Good evening. Today we will be presenting predicting surface roughness using machine learning. Problem statement and dataset. Our project focuses on predicting surface roughness in CNC machining. Getting the correct finish on a part is difficult, and surface roughness affects the part's quality, performance, and even cost. A lot of shops rely on trial and error to adjust machining settings, which is slow and inefficient. For our data, we used a machining surface roughness dataset from Kaggle, created by the Aeronautics Institute of Technology. It includes 2 experiments with over 600 samples combined. The main features we're using are AP, which is the depth of cut, it's measured in millimeters, VC, the spindle speed, it's measured in meters per minute, and F, the feed rate, it's measured in millimeters per revolution. And our target value is RA, which stands for arithmetic mean roughness. RA is the most common surface finish measurement, and it tells us how smooth or rough the machine surface is. That's the value we're trying to predict using machine learning. Overview of workflow. We followed a basic machine learning workflow for this project. First, we defined the prediction tasks using machining settings like AP, VC, and F to predict the final surface roughness of RA. Then we collected the data from Kaggle and imported the XP1 CSV file into Python. For pre-processing, we checked for missing or duplicate data, and luckily the dataset was already clean. We also used the min-max scaling to normalize the features since they're all in different units like millimeters or millimeter per rev and meters per unit. Next, we selected AP and VC and F as our core features because they have the strongest physical and statistical connection to surface roughness. After pre-processing, we trained 3 different models: a linear regression baseline, a random forest model, and a neural network. Data pre-processing and model setup. First, we checked the dataset for any missing values or duplicates, and everything was clean. We used a min-max scaler because our 3 features are in very different units. Scaling puts them all in the same 0 to 1 range. Scaling was also required for neural networks because they train poorly when inputs are in different scales. For our models, linear regression was used as the baseline because it's simple and gives us a starting point. We chose the random forest model because it can naturally model nonlinear machining behavior. For the neural network, we used 2 hidden layers with 32 and 60 neurons, ReLU activation, and the atom optimizer. We also enabled early stopping to prevent the neural network from overfitting. Baseline performance linear regression. Linear regression gave us a MSE score of 0.046. This means, on average, the model's prediction error is roughly that size in squared units. The R-squared score was 62% of the variation in surface roughness. It captures the general trend between the machining parameters and RA, but only in a straight line relationship. Since machining behavior is nonlinear, this model can't fully capture all patterns in the data. It's a good baseline to compare to more complex models.
So now onto the random forest and neural network results. So the random forest model performed the best because it had a mean squared error of 0.022 and an R-squared score of 0.82. And this is because it handles the nonlinear behavior of machining surface roughness really well. And the neural network underperformed compared to the random forest with a mean squared error of 0.049 and R-squared around 0.59. That's because our experiment 1, our first data set, only had around 300 samples and just a few features. So the neural networks need more data to learn effectively. And for the next steps, we're planning to add experiment 2, our next data set, increase the data set size, and include additional features like tool wear, cutting forces, which are related to surface roughness, and applying hyperparameter tuning and trying models like polynomial regression to see if we can boost performance further.